Deep in the constellation of Scutum shines a star so enormous it almost defies the laws of physics, Stephenson 2-18. It's so vast it could swallow our sun millions of times over. How can something that big even exist tonight? We'll explore this cosmic giant and the mysteries that keep scientists awake at night. If you enjoy these journeys, please like, subscribe and share, and tell us in the comments, what do you think could form a star this impossible? Thank you for watching. Now, let's begin. Far from Earth, the Milky Way extends as a vast rotating disk of gas dust and stars. From our position within one of its minor arms, it appears as a pale, luminous band that encircles the night sky, though from above it would look like a spiral of light coiling around a dim central bulge. Each arm is a region where density waves move through interstellar material, gathering gas and triggering the birth of new stars. These arms are not fixed structures, but patterns of motion slowly winding over millions of years, as the galaxy turns once every few 100 million years. Along the inner portion of one such arm lies a region of unusual brightness and obscurity, the Scutum Centaurus arm. Here, dense lanes of dust overlap with stellar nurseries and great clusters of massive stars glow faintly behind the haze. The Scutum region is one of the most active star-forming zones known in the Milky Way. It sits between the galactic center and the Sun's orbit, about 20 to 30,000 light-years from our planet, partly hidden by intervening dust that absorbs visible light. Infrared and radio observations penetrate this obscuration, revealing groupings of massive young and middle-aged stars embedded in molecular clouds. Among them lies a concentration of red supergiants that mark the later stages of stellar evolution in this part of the galaxy. Their presence indicates that millions of years ago a giant burst of star formation occurred here, producing stars so massive that many have already exploded or collapsed. Those that remain glow dimly but enormously, shedding their outer layers in steady glowing winds. From the perspective of a distant observer, the Scutum arm would appear mottled patches of darkness and soft light, where dust filaments twist across faint clouds of ionized gas. Embedded inside are the remnants of earlier generations, their ashes forming the seeds of new stellar birth. It is within this rich complex fabric that the Stephenson 2 cluster rests, almost invisible to optical telescopes yet unmistakable in the infrared spectrum. The Milky Way's structure provides the broad stage on which this story unfolds. Its spiral pattern is not uniform. Near the galactic center, the bar of old stars and gas channels material into the inner regions, feeding star formation in the arms. Beyond that bar in the Scutum Centaurus arm, the density of interstellar matter becomes high enough to trigger the creation of massive clusters. These clusters are the result of gravitational instabilities in giant molecular clouds, vast accumulations of hydrogen and helium that can span hundreds of light years. When such a cloud collapses, it fragments into smaller cores that each form a star. In the densest knots, the pressure becomes great enough to ignite nuclear fusion, and a cluster emerges. Over time, winds and radiation from its youngest, hottest members clear away the leftover gas, leaving behind a gravitationally bound system of stars of many types. The Stephenson 2 cluster is one of these, but its visibility is limited by the thick dust that lines our view through the plane of the galaxy. Observers must rely on wavelengths beyond the visible infrared submillimeter and radio to sense its light. Through these, a detailed picture emerges, a compact group of luminous red supergiants, each many hundreds of times larger than the Sun, each nearing the end of its life. The cluster's existence tells of an earlier generation of intense formation, a burst that produced dozens of extremely massive stars within a relatively short time span. Their combined radiation once illuminated the surrounding region, carving cavities in the interstellar medium, and later their deaths enriched the gas with heavier elements that would form the next generation. The Scutum arm acts as both cradle and archive, containing in its depths the record of countless such cycles. As the galaxy rotates, gravitational forces stir these materials, mixing elements from one arm to another, gradually shaping the composition of future stars and planets. This dynamic balance between birth and decay defines the Milky Way's evolution, yet the process unfolds on timescales so immense that from any human vantage it seems still unchanging and silent. The light from Stephenson 2 and its most massive member, Stephenson 2 to 18, began its journey long before civilization existed on Earth. Across the interstellar medium, photons scatter off dust grains, their paths slightly altered but not erased. By the time they reach telescopes, their wavelengths have stretched, their brightness dimmed, carrying with them information about distance, temperature, and motion. Astronomers extract these clues to map where the cluster lies and to measure its properties. They find that it sits roughly 20,000 light-years away in the direction of the constellation Scutum, a region named for the shield shape imagined by early observers. That shield now hides one of the largest stars known yet. Its discovery was made possible only by instruments that can see what human eyes cannot. The contrast between visible obscurity and infrared revelation is stark. Without modern detectors, the Scutum arm would remain a dark gap in the Milky Way's midsection. Within that darkness, however, the processes that define stellar life continue relentlessly: fusion, expansion, mass loss, and eventual collapse. The region's temperature and density gradients govern how long gas remains stable before it condenses again into new stars. Waves of energy from previous supernovae compress nearby gas clouds, setting off further rounds of star formation, a cascading rhythm that sustains the spiral arms over hundreds of millions of years. The Milky Way itself is not static. It interacts gravitationally with satellite galaxies, pulling in streams of gas and stars that alter its structure. All of these influences converge in regions like Scutum, where conditions favour both the birth of the massive and the death of the luminous. When viewed from afar, perhaps from another galaxy, the Milky Way would appear as a glowing disk with subtle reddish patches marking places where such giants shine through their own dust. The light from these patches is dominated by cool, swollen stars, red supergiants, nearing the end of their existence. Their faint red glow contrasts with the blue light of young hot stars in nearby clusters. Together they form the chromatic balance of galactic life, the youthful and the aging coexisting in quiet motion. Stephenson 2 to 18 belongs to this older population, and though its lifespan is short on cosmic scales, it plays an outsized role in enriching its surroundings. But here at the outset, the focus remains on the broad setting, the spiral arm that shelters it, the quiet rotation of the Milky Way that carries it along the slow dance of stars and dust, within which it has formed and will one day perish. The scale is too large for change to seem immediate. From the human perspective, the Scutum region will look the same for many lifetimes, its subtle patterns shifting only imperceptibly. Yet across millions of years the arm evolves, the clusters drift, and the elements cycle once more through the galaxy's unending current. Within this stillness, Stephenson 218 burns unseen immense beyond measure, waiting to be found. Deep within the Scutum Centaurus arm, where interstellar dust thickens and the visible sky gives way to infrared haze, lies a region of quiet density known as the Stephenson 2 cluster. It does not blaze in visible light like the open clusters of the Orion or Perseus arms. Instead, it glows faintly in longer wavelengths, detectable only through instruments that see beyond the veil of dust. This obscuration, though it hides the cluster from the human eye, preserves it from the full scrutiny of the galaxy's more energetic radiation. The Stephenson 2 cluster is a stellar gathering of rare character, a dense population of luminous red supergiants, each nearing the final stage of its life. Astronomers classify it as one of the richest collections of such stars known in the Milky Way. Its discovery came from infrared surveys that mapped the plane of the galaxy, searching for concentrations of bright sources at these wavelengths. What emerged was a compact, massive cluster whose members shine not with blue or white heat, but with a deep red glow. Their temperatures cool compared with the sun's, yet their luminosities hundreds of thousands of times greater. Each star has expanded to a size that defies ordinary scale, their outer layers tenuously held by gravity, their surfaces restless and extended. Within the quiet heart of the cluster, gravitational attraction binds these giants together, though over millions of years that bond will weaken as stellar winds carry mass away. The cluster's origin traces back roughly 20 million years, when a massive molecular cloud collapsed under its own weight. The pressure and temperature at the densest points rose until nuclear fusion began igniting the cluster's first generation of stars. The most massive among them, those exceeding 20 or 30 times the mass of the Sun, evolved rapidly, burning through their hydrogen fuel in only a few million years. Many have already ended their lives in supernova explosions, scattering heavy elements into the surrounding medium. What remains are the survivors of that initial burst, the slightly less massive stars now swollen into red supergiants. Their ages align closely, indicating a single episode of star formation rather than a prolonged sequence. This simultaneity makes the cluster an ideal laboratory for studying the later stages of massive stellar evolution. Seen through infrared telescopes, the cluster appears as a compact group embedded in faint nebulosity. The concentration of red supergiants dominates the image, but hidden among them are smaller, fainter stars that make up the cluster's background population. These lower mass members, though far less luminous, help define the cluster's total mass and gravitational stability. Estimates suggest that Stephenson 2 could originally have contained more than 10,000 solar masses of material. Over time, stellar winds and radiation pressure have pushed much of this mass outward, forming diffuse clouds that drift through the Scutum region. The environment is turbulent yet serene on human timescales. The winds from one star merge with those from another, forming slow-moving flows that enrich the cluster's outer zones with dust and gas. Interactions among these winds can create bow shocks and shells, subtle structures that reveal the hidden activity in what appears from afar as tranquil red light. Despite the crowding of massive stars, the cluster's density is low enough for each to evolve largely, without direct interference from its neighbours. Gravitational encounters are rare and collisions almost non-existent. The shared field holds them gently like embers suspended in a quiet current. Astronomers study such clusters not only to understand individual stars, but to trace the history of the Milky Way's spiral arms. Clusters like Stephenson 2 mark points of intense star formation that occurred when spiral density waves compressed the interstellar medium. By mapping their ages and locations, scientists reconstruct the timing and motion of those waves, revealing the rhythm of galactic evolution. The Stephenson 2 cluster occupies a region just below the galactic plane, its coordinates aligned with the direction of the constellation Scutum. Though the light that reaches Earth today began its journey 20,000 years ago, the cluster itself has changed little in that span compared with its overall lifetime. The red supergiants continue to cool and expand, their envelopes gradually thinning. Eventually, the cluster will disperse its members, scattering through the disk of the galaxy. For now, it remains cohesive, its identity intact amid the darkness. Inside the cluster, light moves slowly through dust, scattering in long wavelengths that give it a copper-red hue. The space between the stars is filled with fine grains of silicate and carbon, condensed from the winds of earlier giants. These grains absorb ultraviolet and visible radiation, re-emitting it as faint infrared warmth. To an observer equipped with sensitive detectors, the cluster glows with a diffuse smoky radiance. Every photon carries the imprint of its origin, the temperature of the star, the density of its wind, the thickness of the intervening dust. From these patterns, astronomers deduce the physical conditions within the cluster. They find that temperatures of individual red supergiants range between 3,000 and 4,000 degrees Kelvin, while their radii can reach over 1,000 times that of the Sun. Such values, though approximate, illustrate the extremes of size and luminosity found here. Yet even among these titans, one stands apart. At the cluster's edge, faintly detached from the densest grouping, lies a star whose brightness and inferred radius surpass all others. It is designated Stephenson 2-18, sometimes abbreviated as S218, and it challenges the upper limits of what a star can be. Its measured luminosity suggests a radius so large that if placed at the center of the solar system, it would extend beyond the orbit of Saturn. Whether these numbers are exact remains uncertain, for dust and distance complicate every measurement, but the implication is clear: Stephenson 2-18 is extraordinary. Within the calm order of the cluster, it represents an extreme outlier, a body whose sheer scale tests the boundaries of stellar physics. Its discovery, like that of the cluster itself, came through painstaking observation and careful correction for extinction. By comparing its brightness at different wavelengths, researchers determined its temperature and estimated its size, concluding that it is among the largest known stars in the galaxy. The Stephenson 2 cluster thus gained new significance as the home of a supergiant so immense it seems to defy theory. In the larger context of the Milky Way, the cluster remains a faint node in the tapestry of the Scutum arm. Yet for those who study massive stars, it is a key. Here in a single region are gathered examples of stellar evolution at its most powerful and transient. Each red supergiant will soon end in collapse, scattering the materials that once composed its surface into the interstellar medium. These elements, carbon, oxygen, silicon, iron, will seed future generations of stars and planets. The cluster becomes both cradle and grave, a brief moment in the long recycling of matter that defines the galaxy's continuity. Around it, interstellar gas continues to drift, shaped by gravity and the remnants of earlier explosions. In time, the glow of Stephenson 2 will fade, its members no longer recognizable as a single group. But for now, through the haze and distance, their light endures muted, ancient and steady. The emergence of this cluster, its quiet radiance hidden behind dust, marks the beginning of the deeper story. Among its crowded giants, one star waits to reveal how immense and how fragile stellar life can become. Within the dim red congregation of the Stephenson 2 cluster, one particular star emits a glow so deep and so faintly scattered through dust that it almost disappears into the background. Yet measurements across multiple wavelengths show that this faintness is deceptive. Buried behind interstellar clouds and veils of its own expelled matter, Stephenson 2-18 radiates an extraordinary amount of energy, enough to rival or surpass nearly every other known star. Finding and confirming its identity required years of careful observation, comparison, and patient calibration. The challenge begins with the cluster's distance. Around 20,000 light-years separate it from Earth, and the line of sight passes through dense regions of dust and gas along the Milky Way's plane. This dust absorbs and scatters light unevenly, reddening the spectrum and reducing brightness by several magnitudes. Optical telescopes reveal almost nothing. The star field appears blank or mottled with faint traces. Infrared detectors, however, reveal a hidden structure points of light corresponding to stars invisible in the visible spectrum. Within this infrared map, one source stands out as unusually luminous at longer wavelengths, its colour indicating a cooler temperature but extreme radiative output. This is Stephenson 2-18, identified initially through catalogue surveys and later confirmed by spectroscopic analysis. Even so, determining which star corresponds to which catalogue entry proved difficult. Several red supergiants in the cluster share similar brightness and colour, and the heavy extinction creates ambiguity in position and magnitude. Early observations described a handful of potential candidates. It was through cross-matching infrared data with high-resolution spectra that astronomers isolated the true identity of Stephenson 2-18. Its spectral lines, broadened by the star's slow pulsating atmosphere, matched those expected from a red supergiant of exceptional size. The task of measuring such a distant and dust-shrouded object involves layers of inference. Photometry provides apparent brightness at specific wavelengths. Spectroscopy reveals surface temperature and chemical composition. Together they allow estimation of luminosity, which combined with distance yields a rough measure of radius. But each step contains uncertainty. The amount of extinction along the line of sight is not uniform. Dust properties vary, and models of the interstellar medium can differ. Slight errors in extinction correction propagate into large uncertainties in derived size. Some analyses place Stephenson 2-18's radius at around 2,000 times that of the Sun, while others using different assumptions produce slightly smaller values. Regardless of the precise number, all results agree that the star ranks among the most expanded objects known. Locating it among its cluster companions is not simply a matter of coordinates, but of contrast. When observed in narrow infrared bands, the cluster displays subtle differences in brightness, corresponding to temperature and dust environment. Stephenson 2-18 sits near the cluster's edge, slightly offset from the densest concentration of red supergiants. This position may reflect its evolutionary stage or the influence of local dust clouds that have shifted relative to the cluster's centre. From our vantage point, it appears isolated, its faint red halo extending into the surrounding darkness. The star's apparent isolation enhances its mystery. Infrared images show a diffuse glow around it, possibly caused by circumstellar dust formed in its own outflowing wind. That envelope further dims and reddens its light, creating the illusion of distance even within its own cluster. To detect it clearly, astronomers use instruments aboard space-based observatories capable of sensing thermal radiation with high sensitivity. These observations reveal a faint extended structure around the star, evidence of material expelled over thousands of years. Within that diffuse cocoon, light from the photosphere scatters and cools, giving the entire region a subdued uniform glow. Ground-based telescopes complement these data with higher spectral resolution, allowing the identification of molecular bands characteristic of cool supergiant atmospheres: titanium oxide, carbon monoxide, and vanadium oxide. These signatures confirm the star's temperature near 3000 degrees Kelvin, much cooler than the Sun yet far brighter in total energy output. Such measurements not only establish its nature, but also expose the limitations of human perception. What seems dim through a telescope is in reality one of the most radiant sources in the galaxy. Locating Stephenson 2-18 was as much an exercise in removing interference as in detecting signal. Each layer of dust, each calibration bias had to be stripped away through modelling. Astronomers compare its colour indices, the differences in brightness between multiple infrared bands, to theoretical stellar atmospheres. When these indices align with predictions for a red supergiant of known luminosity, the distance and size can be constrained. Yet because the cluster itself suffers from uncertain distance estimates, every conclusion remains bounded by error margins. Some estimates place Stephenson 2 at roughly 6 kiloparsecs from Earth, others closer to 5, and this variation alone alters the calculated luminosity significantly. Still, even the lowest plausible values make Stephenson 2.18 hundreds of thousands of times more luminous than the Sun. Its light diminished by dust and distance remains detectable only through sensitive instruments, yet it dominates the energy budget of the entire cluster. The difficulty of pinpointing such an object illustrates the challenges of galactic astronomy. Unlike nearby stars, those in the inner Milky Way are obscured by overlapping clouds and blended fields. Identifying a single source requires cross-disciplinary cooperation: infrared photometry, spectroscopy, astrometry, and modelling of extinction laws. Each discipline refines the picture until an identity emerges. In the case of Stephenson 2.18, the outcome is remarkable, a confirmation of a red supergiant so vast that theoretical models strain to explain its stability. The process of locating it also reveals the quiet complexity of the Scutum region itself. Between the observer and the cluster lie layers of interstellar matter that shape the light in subtle ways. These layers are not static. They drift, compress, and fragment under galactic tides. Their composition, fine silicate grains, carbonaceous dust, and trace ices determines how starlight is absorbed and re-emitted. Mapping these properties using background stars provides a clearer picture of extinction, allowing corrections that make Stephenson 2.18's intrinsic brightness more accurate. The more accurately the extinction is known, the more confidently the star's size can be inferred. Through this meticulous process, astronomers gradually isolate the signal from noise, revealing the true enormity of what had seemed a modest flicker. The star's position within the cluster also aids understanding of its environment. Red supergiants in Stephenson 2 are distributed unevenly, possibly reflecting slight variations in the original molecular cloud. Some form subgroups while others drift outward under the cluster's gravitational potential. Stephenson 2-18's location near the periphery may mean it is beginning to move away, its mass loss altering its momentum. As its outer layers expand and shed material, stellar wind pressure slowly pushes it outward. Over hundreds of thousands of years, this process could separate it completely from the main cluster, leaving it surrounded only by its own debris. Yet for now, it remains a member of this quiet assembly of giants, its faint red signature one among dozens that together define the infrared profile of the Scutum arm. To human eyes it is invisible, but in the instruments that translate heat into light, it shines as one of the galaxy's grandest anomalies. Its discovery deep within the obscured core of a dusty arm reminds astronomers how incomplete the visible universe is. Much of the Milky Way hides behind its own shadow, and only by looking beyond ordinary sight can the largest and most elusive objects be found. In that hidden realm, Stephenson 2-18 glows quietly, vast and improbable, a point of radiance buried within a cluster of other fading suns. The act of locating it, teasing its signal from the confusion of dust distance and overlapping stars, marks not an end but a beginning, the first step toward understanding how such a giant can exist at all. Measuring the distance to Stephenson 2-18 begins with the faint light that manages to escape the thick curtain of dust between it and Earth. That light, though diminished and reddened, carries within it the information astronomers need to map the star's position in space. The challenge lies not in gathering light, but in interpreting it. Every photon that reaches a telescope has travelled through tens of thousands of light years of interstellar material, passing through clouds whose density, temperature and composition vary unpredictably. Dust grains absorb some wavelengths more than others, making the star appear dimmer and cooler than it truly is. Correcting for this effect, known as interstellar extinction, requires models of how dust interacts with light across the spectrum. Different regions of the galaxy follow slightly different extinction laws, and these differences can shift the inferred distance by thousands of light years. For Stephenson 2018, the estimates depend heavily on which of these models is used. The cluster that surrounds it, Stephenson 2, is generally placed about 20,000 light-years away, but that figure carries uncertainties of several thousand light-years in either direction. Astronomers compare its apparent brightness with that of similar clusters, and with theoretical predictions of how bright a star of its type should be. The method known as spectrophotometric distance measurement converts colour and luminosity into space coordinates. Yet for stars embedded in dust, the corrections are large and small errors multiply rapidly. The same challenge arises when measuring its temperature. A red supergiant spectrum is dominated by molecular bands rather than sharp atomic lines. These features are broad and complex, changing with temperature pressure and the presence of dust around the star. The outer layers of Stephenson 218 are not solid or stable. They expand and contract, shifting the emitted light in subtle ways. The temperature derived from one wavelength range may differ from that derived from another. Observations in the near-infrared indicate a surface temperature near 3000 degrees Kelvin, but models that account for dust scattering suggest it might be slightly higher. Even a difference of a few hundred degrees changes the estimated radius significantly. This interplay between brightness, temperature and distance forms a triangle of uncertainty that defines all knowledge of the star. To calculate its size, astronomers use the Stefan-Boltzmann relation, which connects luminosity, temperature and radius. But each term depends on measurements that are themselves uncertain. If the star is slightly closer than assumed, its luminosity decreases. If it is slightly hotter, its radius contracts. Conversely, if the extinction is underestimated, both luminosity and size inflate. The result is a range of possible radii extending from about 1500 to over 2000 solar radii. In either case, the scale defies comprehension. At the smallest plausible value, the star would still extend beyond the orbit of Jupiter if placed at the centre of the solar system. At the largest, it would reach past Saturn. The light we see today left the star during a time when the last ice age was beginning on Earth. That light began as energy deep in the stellar core generated by nuclear fusion and rising through layers of gas before escaping into space. Each photon underwent countless scatterings within the star's atmosphere, losing direction but retaining its energy signature. By the time it entered interstellar space, it carried the fingerprint of a massive cool surface radiating across the infrared spectrum. Through telescopes, that radiation appears faint and featureless, yet when passed through spectrographs, it reveals absorption bands and subtle shifts that betray motion, rotation, and chemical composition. In this way, light becomes a messenger not only of distance, but of the star's physical state. The uncertainty that surrounds Stephenson 218's measurements is not a sign of ignorance, but of the difficulty of observing such extremes. Massive red supergiants push the boundaries of existing models. Their extended atmospheres blur the distinction between surface and space. Light from the deeper, hotter layers mixes with that from cooler outer regions, producing a composite spectrum that no single temperature can represent. dust in the circumstellar envelope further modifies this spectrum by absorbing and re-emitting radiation. Some of that dust is newly formed, condensed from gas expelled in the star's own wind. As the dust cools, it radiates at mid-infrared wavelengths, creating a faint halo that adds to the apparent brightness. Untangling these overlapping sources demands careful calibration, using stars of known properties as reference points. Even then, the results must be expressed as probabilities rather than certainties. The same is true for velocity measurements. Astronomers use Doppler shifts in spectral lines to determine how fast the star and its cluster move relative to the Sun. Those velocities, combined with models of galactic rotation, provide another way to estimate distance. In the case of Stephenson 218, the observed radial velocity aligns with that expected for an object about 6 kiloparsecs away, consistent with other indicators. Yet this method also depends on assumptions about how the Milky Way's inner regions move, and those models evolve as more data are collected. Thus, every refinement in galactic mapping slightly alters the star's inferred position. The interplay of light and uncertainty extends to luminosity itself. For most stars, luminosity can be calculated directly from distance and brightness. But for red supergiants surrounded by dust, some of the energy escapes as thermal radiation, rather than visible or near-infrared light. Accounting for this hidden component requires integrating observations across multiple wavelengths, from optical through infrared to sub-millimeter. Space telescopes such as Spitzer and Herschel have provided data that fill these gaps, showing that much of the star's true output lies in the far infrared re-emitted by dust grains, at temperatures of a few hundred degrees Kelvin. When this is included, the total luminosity of Stephenson 218 exceeds 200,000 times that of the Sun, confirming its status as one of the galaxy's brightest red supergiants. Yet even this figure depends on assumptions about distance and extinction. The more precisely those can be constrained, the more securely its position on the Hertzsprung-Russell diagram can be defined. These uncertainties are not flaws but reflections of the star's environment and our vantage point within the galaxy. The Milky Way's disk is opaque along many lines of sight, and its dust distribution is neither smooth nor predictable. Between Earth and the Scutum arm, numerous clouds intersect, each adding or removing a fraction of the total extinction. Some of these clouds contain complex organic molecules and icy mantles that alter how light is absorbed. The cumulative effect produces irregular attenuation that cannot be fully corrected with broad models. Only direct observation across multiple wavelengths can approach accuracy, and even then the values fluctuate as instruments improve. In this sense, the study of Stephenson 218 is as much about refining methods as about the star itself. Each attempt to measure it pushes the boundaries of how astronomers interpret faint dust-obscured light. The uncertainties will narrow with future missions that measure parallax directly, but for now, they remain part of the story, a reminder that every image of the universe is filtered through distance, matter, and time. What is certain, despite all correction and recalibration, is that Stephenson 218 stands near the upper limit of known stellar size and brightness. Its presence confirms that the Milky Way still harbours extremes unseen in ordinary skies. The light that carries this information continues its journey through space, crossing the silent gulf from a cluster hidden in the Scutum arm to a telescope mirror on Earth, where it ends its long flight as a single point of red in an otherwise invisible field. That point contains everything we know and everything we question, a beacon defined as much by uncertainty as by brilliance. Among all the stars within the Stephenson 2 cluster, Stephenson 218 occupies an extreme unlike any other, a scale so vast that even its smallest possible measurement stretches the limits of theory. Astronomers describe its radius in terms of solar multiples, but numbers alone fail to convey its enormity. If placed at the centre of the solar system, the outer boundary of its tenuous atmosphere would extend well beyond the orbit of Saturn. Its light, diluted by dust and distance, reaches Earth as a faint reddish whisper, yet in its own region of space the star shines with a luminosity hundreds of thousands of times greater than that of the Sun. At such magnitude, energy pours from every layer of its atmosphere in a constant slow flood. Despite this, the surface appears cool around 3000 degrees Kelvin, its colour a deep subdued crimson. The apparent contradiction between intense luminosity and low temperature arises from its size. The greater the area of the radiating surface, the lower the energy each part must emit to produce such brilliance overall. This is the hallmark of red supergiant stars that have swollen in their final stages, their outer envelopes expanding to such vastness that gravity barely holds them. The gas at the surface is so thin that a spacecraft could move through it without resistance, yet from a distance it forms a continuous luminous sphere. Within this swollen shell, convection dominates. Hot plasma rises slowly from inner layers, cools and sinks again, creating cells so large they could span the distance from the Sun to Earth. These convective motions sculpt the star's surface into shifting regions of brightness and shadow. No solid crust exists, only turbulence and radiative flow. The entire outer atmosphere moves in slow motion, expanding and contracting over months or years, giving rise to minor variations in brightness that astronomers detect as gentle pulsations. Such behavior indicates a delicate balance between gravity and pressure, a balance that becomes harder to sustain as mass loss increases. Estimates suggest that Stephenson 2-18 loses material at a rate millions of times higher than the Sun, casting its outer layers into space as a steady wind of gas and dust. This wind forms the faint halo seen in infrared images, an envelope that blurs the star's edge and contributes to its apparent size. The atmosphere does not end sharply, but merges gradually with the surrounding medium, fading into a region where molecules begin to form and dust condenses. In that transitional zone, radiation from the star interacts with the outflowing material, shaping it into arcs and shells that expand outward over centuries. Each layer records a phase of the star's recent history, a physical trace of instability and release. To understand how such a giant maintains its form, astronomers turn to models of stellar structure. These show that as a massive star exhausts hydrogen, in its core fusion moves outward into surrounding shells. The core contracts and heats while the outer layers respond by expanding. The result is a star with a dense hot interior and an enormous cool exterior. Pressure from radiation and convection supports the outer envelope, but as mass loss increases, that support weakens. Eventually, gravity and pressure reach an equilibrium so fragile that minor disturbances can alter the star's shape or trigger further expansion. In Stephenson 2-18, this equilibrium has produced a radius so large that the usual definitions of a stellar surface no longer apply. Astronomers describe the star's photosphere not as a fixed boundary, but as the layer from which most visible and infrared light escapes. Above it, temperatures and densities fall until molecules form and radiation diffuses freely. The scale of this transition region can span hundreds of solar radii. When instruments record the star's brightness, they capture an average across these depths, blending emission from multiple layers into one composite value. This blending makes precise measurement nearly impossible. Still, the data agree on one point: Stephenson 218 lies near the physical limit at which a star can remain stable without tearing itself apart. At sizes beyond a few thousand solar radii, the surface gravity becomes so weak that material can escape with little energy. The outward pressure from radiation nearly balances the inward pull of gravity, creating a condition close to the Eddington limit, where further luminosity would drive catastrophic mass loss. That Stephenson 218 exists at all suggests it hovers just below this threshold, shedding mass steadily, but not explosively. The mass of the star itself remains uncertain. Models based on its luminosity suggest an initial mass of around 40 to 50 solar masses, though it has likely lost a significant fraction through winds. As its mass declines, so does its gravitational binding, accelerating further loss. This feedback loop defines the late life of a red supergiant. As it brightens and expands, it becomes more fragile, and as it loses matter, it becomes even more extended. The balance persists for only a brief cosmic moment before collapse. Observing such a star offers a rare glimpse into this fleeting stage. Theoretical limits predict that red supergiants cannot exceed about 2,000 solar radii without becoming unstable. Yet Stephenson 218 appears to approach or surpass that boundary. The uncertainties in distance and temperature leave room for revision, but the possibility remains that it occupies a regime few stars can reach. This has implications for understanding stellar evolution at extreme masses. If such giants are more common than previously thought, they could influence how heavy elements are distributed in the galaxy, since their winds and eventual explosions contribute large quantities of material to the interstellar medium. Even now, Stephenson 218 may be enriching its surroundings with complex molecules and dust grains that will one day become part of new stars and planets. The scale of its influence extends far beyond its visible light. Around such a star, the gravitational field is gentle at the surface, and sound waves move slowly through the gas. Each convective cell rises and falls over months, releasing energy in deep rolling cycles. To any hypothetical observer nearby, the view would be dominated by a horizonless expanse of red and orange rippling with slow currents and glowing softly through translucent haze. Above, faint arcs of dust drift outward, reflecting the light that escapes from below. This is not a violent environment, but a vast and quiet one, its movements measured in centuries. Yet beneath that calm surface, nuclear fusion continues at immense rates, consuming helium and heavier elements in nested shells around the contracting core. The star's energy output remains steady, but its structure grows increasingly delicate. As mass loss proceeds, the envelope will continue to expand and thin the outermost layers, dispersing into interstellar space. Eventually, only the dense core will remain, setting the stage for collapse. For now, however, the star endures in balance, its impossible proportions sustained by the precise interplay of forces that govern all stars stretched to their outermost limits. Stephenson 218 stands as both an object of measurement and a boundary of comprehension. Its scale challenges the language used to describe stars, demanding comparisons not to the Sun but to entire planetary systems. It is at once a single point in the galaxy and a vast domain unto itself, an atmosphere larger than imagination glowing faintly behind the dust of the Scutum arm. Within that quiet immensity, the physics of energy and gravity reach equilibrium, and for a brief span in cosmic time, the universe allows something this vast to exist. The surface of Stephenson 218 is not a fixed boundary, but a region of transition where the gas thins, light escapes, and the line between star and space dissolves. Its temperature, roughly 3,000 degrees, Kelvin, gives it a deep red hue in visible wavelengths and a brighter glow in the infrared. This surface, known as the photosphere, is a vast unstable ocean of convective motion. Enormous currents of plasma rise slowly from the layers below, release their heat, and sink again in cycles that can take many months. Each convective cell may span hundreds of millions of kilometers large enough to engulf the orbit of Earth several times over. These currents churn ceaselessly, shaping the surface into shifting zones of brightness and shadow. To human eyes, if one could somehow approach without being vaporized, the star would appear mottled and restless with dark patches where cooler gas descends and brighter regions where fresh energy wells up from below. Yet the motion would be so slow that it would seem almost still a moving calm stretched over incomprehensible scale. Unlike the Sun, whose surface granulation is fine and rapid, the outer layers of a red supergiant are governed by a delicate balance between convection and radiation. The gas density is so low that photons travel long distances before interacting with matter. Energy leaks outward as both radiation and rising material flow. The pressure at the photosphere is only a fraction of that in Earth's atmosphere, so low that a spacecraft passing through would find little resistance. Here the star's gravity is weakened to the point where it barely restrains the gas, and the difference between atmosphere and stellar wind becomes one of definition rather than structure. Above the photosphere, the gas continues to expand and cool, forming an extended atmosphere that reaches many stellar radii beyond the visible disk. Within this vast envelope, molecules form titanium oxide water, vapor carbon monoxide, absorbing and emitting radiation that gives the spectrum its characteristic patterns. These molecular bands make precise temperature measurement difficult, but also provide a window into the chemistry of the outer layers. Infrared observations reveal that the effective temperature across the surface is not uniform. Regions of higher brightness indicate localized upwellings of hot gas, while darker patches mark cooler areas where material is descending. These differences can reach several hundred degrees, producing variations in the observed spectrum depending on which hemisphere is visible. Over time, the convective pattern changes, giving rise to slight fluctuations in brightness. Astronomers record these as semi-regular variations, evidence of the star's slow pulsation. The amplitude is small compared with its total luminosity, but it signals internal adjustments as energy output and envelope structure evolve. Such pulsations are common among red supergiants, the natural consequence of their immense size and fragile equilibrium. They act like the slow breathing of a living organism driven by alternating compression and expansion deep within the star. The temperature also governs the color of the light that escapes. At around 3000 degrees Kelvin, the peak of emission lies in the infrared, with only a faint tail extending into visible red. This is why, even if Stephenson 218 were unobscured by dust, it would appear as a dull reddish star rather than a brilliant point of white or blue. Yet that faint colour belies an immense energy output. Because of its surface area, the total radiation emitted each second is enormous enough to equal hundreds of thousands of suns combined. The interplay between temperature, luminosity and size defines its position on the Hertzsprung-Russell diagram near the uppermost corner reserved for the largest and coolest stars. This region marks the end stage of hydrogen and helium burning in massive stars, where fusion continues in concentric shells, and the outer layers have expanded to extremes. The surface of Stephenson 218 is also a site of constant loss. The same convective currents that bring energy to the surface lift gas high enough for it to escape the star's gravity. Radiation pressure acting on dust grains accelerates this outflow, producing a continuous wind that carries mass away into space. As the gas expands, it cools further and molecules condense into solid particles. These grains form near the upper atmosphere and are pushed outward by the light itself, a slow dispersal that shapes the circumstellar environment. The rate of loss is uncertain, but is believed to be substantial, perhaps 1,000,000 times greater than that of the Sun. Over time, this process erodes the star's outer envelope, thinning it and altering its balance. What appears as surface texture is therefore not static detail, but the visible signature of ongoing change. High-resolution imaging of other nearby red supergiants such as Betelgeuse provides analogues for what may occur on Stephenson 2.18's surface. Observations show giant convective plumes, some extending far above the photosphere, releasing material into space. While Stephenson 2.18 is too distant for such detail to be resolved directly, the same physics applies. Its atmosphere must be filled with similar structures, slow eruptions that lift gas outward, forming arcs and filaments. Over centuries, these flows merge into the smooth envelope detected in infrared light. The entire star can be thought of as a slow-motion storm, each part feeding energy into the next, maintaining balance through ceaseless circulation. Temperature variations also affect the chemistry of the surface. In hotter zones, certain molecules break apart. In cooler regions, they reform. This dynamic equilibrium produces a complex spectral fingerprint that shifts over time. By studying these changes, astronomers learn not only about temperature, but also about the composition of the star's outer layers. Elements such as oxygen, carbon, and silicon appear in molecular form, revealing the stages of nucleosynthesis that occurred earlier in the star's life. Each molecule carries the memory of reactions deep within the core, now transported outward by convection and released into the atmosphere. Thus, the surface becomes both a mirror and a messenger, displaying on its vast canvas the internal processes hidden far below. Despite its cool temperature, the star emits a significant portion of its radiation as visible light because of its sheer size. The light that escapes must traverse the circumstellar envelope, and the interstellar dust beyond emerging at Earth heavily reddened. Correcting for this effect reveals its intrinsic colour, slightly orange rather than deep red, indicating a true temperature slightly above the measured effective value. The subtlety of this correction underscores how fragile such measurements are. A small error in extinction leads to large changes in inferred temperature. Nonetheless, the overall picture remains consistent. Stephenson 2.18 is one of the coolest and largest luminous stars known. In this regime, small differences in temperature have profound effects on structure. A decrease of a few hundred degrees can cause the atmosphere to expand dramatically, while a similar increase can trigger partial contraction. These adjustments occur slowly over years or decades as the star seeks equilibrium. Each oscillation releases or absorbs energy, contributing to the variability observed from afar. Such cycles mark the gradual transformation from stability toward the end stages of stellar life. The surface of Stephenson 2-18, though vast and tranquil in appearance, is the visible frontier of that transformation. It is where internal fusion radiation and gravity converge in fragile balance. The temperature defines not only its colour but its destiny, determining how long the envelope can resist collapse, how quickly it loses mass, and how it will eventually die. In the quiet glow of its surface lies the record of that slow evolution, a story written in light too faint to see but enduring across thousands of years as it travels from the Scutum arm to our telescopes, carrying with it the warmth of a dying giant. Beyond the visible photosphere of Stephenson 2.18, the star's substance continues outward in a tenuous flow that no longer behaves like a bound atmosphere. The boundary between star and space becomes fluid here, a slow, steady outpouring of gas that drifts into the surrounding darkness. This is the stellar wind, a movement of matter, driven by radiation pressure, convection, and pulsation. It carries away the products of the star's inner life atoms, forged in fusion and dust, condensed from cooling gas, spreading them through the interstellar medium. The rate of this loss is staggering. The star sheds material equivalent to the mass of the Earth every few years. To the eye of a distant observer, the wind forms an envelope that glows faintly in the infrared, a halo of dust and molecules that absorbs light from below and re-emits it at longer wavelengths. This outer atmosphere is neither uniform nor calm. It is a restless sea of expanding gas where waves of density rise and fall as the underlying star breathes. In this vast region, temperatures drop from thousands of degrees near the surface to a few hundred farther out, cool enough for molecules to survive and condense. Observations of similar red supergiants show that the density declines gradually rather than sharply, producing layers of differing composition. Closer in, the gas remains mostly atomic, but as it expands and cools, it transitions into molecular hydrogen, carbon monoxide, and silicate dust. Each stage marks a step in the transformation of stellar material into interstellar matter. The wind from Stephenson 2-18 does not flow smoothly. It clumps, forming knots and arcs shaped by magnetic fields and turbulent motion. Such irregularities are expected in stars of this size, where convection on the surface feeds instabilities into the outflow. Massive cells of hot gas rise and burst through the photosphere, injecting localized surges of material into space. These surges collide with slower streams, generating shock waves that compress and heat the gas before it cools again. Over time, this cycle builds shells around the star, each representing an episode of enhanced mass loss. Though individual events may be invisible from Earth, their cumulative effect creates a stratified structure detectable in the infrared and submillimeter bands. Instruments that map thermal emission reveal these shells as faint rings expanding outward at speeds of a few tens of kilometers per second. They are relics of the star's changing rhythm, the physical traces of its internal pulsations. The energy that drives this wind originates deep within the star's convective layers. Radiation exerts outward pressure on particles of dust and gas, while pulsation provides the mechanical lift that allows matter to escape gravity. As the gas rises and cools, it condenses into dust grains composed of silicates and aluminum oxide. These grains absorb stellar photons and are accelerated outward, dragging surrounding gas with them through collisions. The process is self-sustaining. More dust forms as material moves away, increasing the efficiency of radiation pressure. The result is a slow but powerful flow that extends many astronomical units from the star before merging with the interstellar environment. In this region, chemistry becomes rich and diverse. Molecules break apart and reform under the influence of ultraviolet light from nearby stars. Complex species such as silicon monoxide and water vapor emerge, precursors to the minerals and ices that will one day exist in new planetary systems. The outflow of Stephenson 2-18 thus represents not only loss, but creation, a quiet dispersal that seeds the galaxy with the building blocks of future worlds. The scale of this envelope defies simple description. Its radius may exceed several times the size of the visible star, encompassing a volume vast enough to enclose the entire solar system many times over. Within it, light from the core is scattered in countless directions, softening the glare and producing a diffuse glow that masks the true edge of the star. To instruments sensitive to mid-infrared radiation, this region appears as a warm cloud, bright near the center and fading outward into the dark. Each photon recorded from this cloud has been absorbed and re-emitted, its path altered by encounters with dust. From these data, astronomers reconstruct the mass loss history and density profile of the wind. They find that the flow is continuous, but variable, shaped by both internal pulsations and external forces. The cluster environment also plays a role. Winds from neighbouring red supergiants interact, creating overlapping regions of shock and compression. The combined effect may form a larger bubble around the entire cluster, a reservoir of enriched gas destined to mix with the interstellar medium. In this way, Stephenson 218 participates in a collective process that extends far beyond itself. Its wind, though personal to the star, becomes part of a communal current of matter circulating through the Scutum arm. Each grain of dust that drifts outward carries with it atoms once buried deep in the stellar interior: oxygen, silicon, carbon, and magnesium. These elements, products of billions of years of cosmic evolution, are now released back into space to begin the cycle anew. Over millions of years they will be swept into new clouds, condensed into new stars, and perhaps into rocky planets orbiting their light. The quiet wind of Stephenson 218 is thus a bridge between generations of cosmic matter, linking the birth of stars to their eventual renewal. At such enormous scales, the dynamics of the wind slow almost to stillness. Speeds of 20 or 30 kilometers per second translate into decades before noticeable expansion. Yet over thousands of years, the envelope grows its outer boundary, moving steadily outward. Within that envelope, densities drop so low that a cubic centimeter contains only a few thousand atoms, but on cosmic terms that is dense enough to glow. The faint infrared radiation it emits is the last trace of the star's own energy diffusing into space. For astronomers, these emissions are clues to both present and future. By measuring their intensity and distribution, they estimate how much material the star has already lost and how long it can continue before collapse. The answers are uncertain, but the direction is clear. The envelope will thicken, the outflow will accelerate, and eventually the outer layers will be gone. In this extended atmosphere, time stretches. Processes that would last seconds on Earth unfold over centuries. Molecules drift apart, collide, and combine again. Dust grains grow by accretion, merging into larger particles that eventually escape the star's influence. Radiation from the cluster and from the Milky Way's ambient field gently warms them, keeping them aglow even as they move farther away. Somewhere at the edge of detectability, the material from Stephenson 218 fades into the general background of interstellar dust, indistinguishable from that of other stars. Yet its origin remains recorded in isotopic ratios, tiny differences in composition that tell of their birth in a red supergiant's wind. These traces, when later incorporated into new stars, will reveal to future observers that the matter they study once flowed from this colossal source. The outer atmosphere and wind of Stephenson 218 thus form both veil and testament, a veil that hides the true star from view, and a testament to the forces that sustain and eventually destroy it. The quiet flow of gas outward represents the slow unmaking of a giant, the return of stellar substance to the galaxy from which it came. For now, the process continues in near silence, unnoticed, except by instruments tuned to the faintest heat. Each second, countless particles depart, drifting outward into the cold, their journey marking the beginning of the star's end. As the wind from Stephenson 218 drifts outward and cools it, becomes the birthplace of dust and molecules that will one day merge with the interstellar medium. This process begins where the temperature in the outflow falls below the condensation point of certain elements. In these distant regions, only a few stellar radii above the visible photosphere gas, composed primarily of hydrogen, helium, oxygen, and silicon, starts to form simple molecules. These molecules act as seeds for the growth of dust grains, these solid particles that make up much of the visible structure of galaxies. At first, the particles are small clusters of a few atoms bonded together by electrostatic attraction, but as they collide and merge, they grow larger, evolving into silicate and oxide grains that can scatter and absorb light. This transformation marks a turning point in the life of the star. What was once pure radiation and gas becomes something tangible, a fine mist of mineral dust floating in space. The creation of dust depends on a delicate balance of temperature, density, and radiation. If the gas cools too quickly, molecules condense into irregular shapes that can be destroyed by subsequent heating. If it remains too hot, dust cannot form at all. Around Stephenson 2-18, conditions appear to favour slow sustained condensation. The wind speed is modest, only a few tens of kilometres per second, allowing time for molecules to combine before being carried too far away. Infrared observations reveal the signatures of silicate grains, particularly magnesium and iron silicates, as well as traces of aluminum oxide and carbon-bearing compounds. These materials absorb ultraviolet and visible light from the star and re-radiate it in the mid-infrared, producing a smooth thermal glow. The spectrum of that glow provides clues to the size and composition of the dust grains, confirming their origin in the cooling outflow of the supergiant. Dust formation is not uniform. It occurs in arcs, plumes, and irregular knots that correspond to zones of higher density in the wind. These clumps arise from the convective instability of the surface below, where giant upwellings of gas periodically release bursts of material. Each burst becomes a separate pocket of dust formation, expanding outward like ripples from a slow explosion. Over centuries they merge into the continuous envelope seen in observations, but their fingerprints remain in the uneven brightness of the star's surrounding cloud. The newly formed dust has a dual role. It not only cools the gas by radiating energy away, but also accelerates the wind by absorbing momentum from the star's light. As photons strike the grains, they impart a tiny push, which, multiplied by countless particles, drives the outflow faster and farther. In this way, radiation sustains the very process that dims the star's light. The more dust forms, the more efficiently it carries material into space, and the more obscured the star becomes. Eventually, the envelope becomes optically thick, meaning light from the inner regions cannot pass through without being absorbed and re-emitted. To distant observers, Stephenson 2-18 appears fainter and redder than it truly is, its brilliance hidden behind its own creation. The composition of this dust is typical of oxygen-rich stars dominated by silicates rather than carbon. Spectroscopic data show strong features at wavelengths associated with stretching and bending vibrations of psi-O bonds, confirming the presence of minerals similar to olivine and pyroxene. In addition, weaker bands indicate the presence of aluminum oxide, one of the first compounds to condense as gas cools. These grains serve as the initial scaffolding on which more complex silicates grow. The chemistry of this environment is controlled by temperature gradients and the availability of free oxygen. Nearer the star, conditions favour oxides. Farther out, carbon monoxide formation ties up most carbon atoms, leaving oxygen to dominate the remaining reactions. The result is a wind filled with tiny reflective crystals that scatter the star's infrared light in every direction. The density of these grains diminishes with distance, but their influence persists for thousands of astronomical units, shaping the spectral energy distribution of the star as seen from Earth. In time, the dust merges with the diffuse molecular material that fills the cluster's interior. Winds from neighbouring red supergiants add their own contributions, and collisions between these outflows create shocks that compress and mix the gas. The cumulative effect is the formation of a local molecular cloud, a loose expanding shell of material enriched with heavy elements. Within this cloud, temperatures drop to a few tens of degrees above absolute zero cold, enough for molecules like carbon monoxide and water to remain stable. These clouds mark the earliest stage of a cycle that may one day lead to new stars. The heavy elements expelled by Stephenson 2-18 will eventually seed future generations of stellar systems, embedding within them the products of the star's long fusion history. This quiet process of recycling connects the death of giants with the birth of new suns. From an observational standpoint, the dust around Stephenson 2-18 provides a valuable laboratory for studying stellar mass loss. The way it absorbs and emits radiation allows astronomers to calculate the temperature profile and density gradient of the wind. Models show that dust formation begins at temperatures between 1000 and 1500 degrees Kelvin, corresponding to regions about 10 to 20 times the stellar radius. Beyond this zone, dust dominates the opacity, and the flow becomes largely radiatively driven. The grains absorb more light as they grow further, enhancing the outflow. Eventually, they drift beyond the region, where they can be heated, effectively cooling to a few hundred degrees and blending with the ambient medium. These outermost layers may persist long after the star has ended its life, expanding into interstellar space as faint echoes of its existence. The presence of dust also affects how the star will evolve. As mass is lost, the outer envelope becomes thinner, altering the balance between pressure and gravity. The reduced mass lowers the escape velocity at the surface, making it easier for additional material to leave. Over time, this accelerates the depletion of the outer layers. The dust, while facilitating this process, also shields the inner regions from radiation, creating a feedback system that can prolong the star's visible life. In essence, Stephenson 2-18 is surrounded by the product of its own decline, a cocoon that both hides and sustains it. To human imagination, this may resemble a self-made shroud, though in reality it is a natural consequence of physics at cosmic scales. At larger distances, the dust merges seamlessly with the diffuse emission of the Scutum arm, contributing to the general glow of the Milky Way's inner disk. From there, it becomes indistinguishable from the countless other grains born in the deaths of massive stars. Each carries isotopic signatures of its origin, and some of these may eventually find their way into meteorites or planetary crusts, where scientists can trace their lineage back to ancient supergiants. In this way, the quiet dust that now surrounds Stephenson 2-18 becomes part of the matter from which life elsewhere may someday arise. For now, it drifts outward in silence, cooling as it moves away, its faint warmth detectable only by the most sensitive instruments. It marks the boundary between star and space, between the present life of a giant and the raw material of future worlds, a bridge of dust and molecules stretching across the darkness. Stephenson 2-18, like most red supergiants, does not shine with unchanging steadiness. Its immense size and fragile equilibrium give rise to slow variations in brightness, color, and temperature that unfold over months or years. To distant observers, these changes appear as faint pulses in infrared light, almost imperceptible when compared with the vast energy it emits. Yet they are crucial, for they reveal the restless nature of a star balanced on the edge of instability. Variability in such a giant is not caused by rotation or eclipsing companions, but by pulsation, global oscillations of the star's outer layers, responding to shifts in internal pressure. As energy flows outward from the core through convective zones, it heats and expands the outer atmosphere. When expansion reduces density, pressure drops, gravity pulls inward again, and the cycle repeats. The result is a slow rhythm of breathing, a pattern too subtle for the naked eye, but visible in the steady record of photometric monitoring. Observations of similar stars show periods ranging from hundreds to a few thousand days, and Stephenson 2-18 likely follows this pattern, though its distance and obscuration make precise measurement difficult. Its brightness may vary by only a fraction of a magnitude, but even that small fluctuation corresponds to vast movements of material across regions billions of kilometers wide. Instability arises naturally in an object of such proportions. The outer envelope of a red supergiant is dominated by convection rather than radiation. Hot gas rises and cools over immense distances, creating zones of turbulence that continually distort the surface. These convective flows do not operate in isolation. They interact with pulsations, reinforcing or damping them in complex ways. Sometimes the two processes align, producing larger amplitude changes and enhanced mass loss. At other times they cancel each other, yielding long periods of apparent calm. This interplay produces irregular variations, the kind often seen in long-period variable stars. For Stephenson 2-18, whose envelope is extremely extended and dilute, the result is likely a semi-regular pattern, punctuated by sudden episodes of increased outflow. The star's atmosphere responds like a slow-moving tide, never entirely at rest. The physical origin of these oscillations lies in the key mechanism, the same process that drives pulsations in many luminous stars. In regions where certain ions, particularly of hydrogen and helium, partially recombine, opacity increases as the gas is compressed. This traps radiation, causing the layer to heat and expand. When it expands, the gas becomes more transparent, radiation escapes, and the layer cools, contracting again. The cycle creates a self-sustaining wave that travels through the star's outer layers. In a red supergiant, these waves have enormous wavelength comparable to the radius of the star itself, and move with slow, stately regularity. The amplitude of the pulsation depends on how energy is transported and on the structure of the envelope. For Stephenson 2-18, with its low surface gravity and strong convective currents, the oscillations may be large enough to modulate both the brightness and the rate of mass loss. Variability in brightness also arises from changing conditions in the circumstellar dust. As the star ejects material, new dust forms and temporarily increases extinction, dimming the light we see. When the dust disperses or moves out of the line of sight, the star brightens again. These external variations blend with internal pulsations, producing complex light curves that challenge analysis. Long-term monitoring in the infrared reveals fluctuations that cannot be explained solely by stellar pulsation, indicating that dust formation events play a significant role. The two processes are linked. Pulsations lift gas into cooler regions where dust can condense, while dust-driven winds feed back on the atmosphere, altering its structure and possibly the timing of the next pulse. Over centuries, these interactions sculpt the outer envelope into an evolving mosaic of density and temperature, a dynamic landscape rather than a static shell. At such low surface gravity, even modest pulsations have dramatic consequences. A small outward motion at the photosphere can lift material beyond the escape velocity, initiating mass loss. As each cycle repeats, the star gradually sheds its outer layers. The rate of loss may vary from one period to the next, creating arcs and shells of gas observable in the far infrared. The wind is not continuous but modulated by the internal rhythm of the star. Some red supergiants exhibit quasi-periodic mass loss episodes separated by decades. Stephenson 2-18 may do the same, though the timescales are blurred by distance. Each episode adds a new layer to the circumstellar envelope, preserving a record of the star's variability over millennia. Instability is also evident in the velocity fields measured by spectroscopy. The absorption lines in the spectrum shift slightly as the atmosphere moves in and out, and their shapes broaden under the influence of turbulence. These shifts correspond to velocities of a few kilometers per second, insignificant compared to the overall mass of the star, but revealing of its internal motion. The spectral profile changes subtly over time, confirming that the surface layers are in constant flux. The motions are slow yet vast, involving masses greater than entire planets. The overall luminosity remains steady within narrow limits, because the energy output of the core changes little, but how that energy escapes varies from moment to moment. This instability is not a flaw, but a natural phase of stellar evolution. As hydrogen and helium fusion proceed in shells around the contracting core, the structure of the star becomes increasingly stratified. Energy must traverse zones of differing density and composition, and any imbalance can trigger oscillations. The star's outer layers act as a resonant cavity, amplifying particular modes of vibration. When conditions shift, perhaps due to changes in fusion rate or mass loss, the frequency of pulsation adjusts. Such transitions may account for long-term trends in brightness seen in other supergiants. For Stephenson 218, whose envelope is exceptionally extended, even slight perturbations can propagate as global waves lasting decades. Variability also hints at the approaching end of stability. As the envelope becomes thinner, the coupling between radiation and matter weakens. Convection becomes less efficient at carrying energy outward, leading to localized overheating and further pulsation. Eventually, these instabilities will grow large enough to destabilize the entire outer region, paving the way for more violent mass loss. Some red supergiants enter a phase of chaotic variability shortly before collapsing their brightness, flickering irregularly as the balance between gravity and pressure fails. Whether Stephenson 2-18 has reached this stage remains uncertain, but its slow pulsations suggest it is well along that path. Despite these immense processes, the star's variability unfolds on timescales too long for direct human perception. Generations could pass before any significant change in brightness is visible without instruments. The calm appearance we see is therefore an illusion born of distance and duration. Beneath that calm, the star is in constant motion, every particle participating in the slow rhythm of expansion and contraction. Its light, travelling across tens of thousands of years, carries the integrated signature of these oscillations, averaging countless cycles into a single steady glow. Only through careful measurement over long periods can astronomers tease out the subtle patterns buried in that glow. In the context of the Stephenson 2 cluster, this variability has broader implications. The collective winds of its red supergiants interact, and the periodic nature of their mass loss may influence the surrounding medium. Shock fronts from overlapping outflows compress gas and dust, potentially triggering new star formation in the region. Thus, the instability of one star contributes to the ongoing evolution of the cluster itself. Stephenson 2-18's variability is therefore not an isolated phenomenon, but part of a network of feedback mechanisms that shape the environment on galactic scales. In the end, the star's small flickers of light record the tension between order and collapse. Each pulse is a negotiation between gravity trying to draw matter inward and radiation insisting on release. The balance still holds, but only barely. The instability of Stephenson 2-18 reveals that even the largest of stars lives on the threshold between being and dispersal, sustained by forces that are momentarily in harmony but destined to drift apart. Its quiet variability is the final heartbeat of equilibrium before transformation begins. Beneath the luminous surface of Stephenson 2-18 lies a realm that cannot be seen, only modelled. No light escapes from the inner zones, yet the faint radiation that reaches Earth bears the imprint of the structure hidden within. The physics governing such a star is understood through equations that describe balance inward gravity countered by outward pressure, heat generated by nuclear fusion carried upward through radiative and convective layers. In ordinary stars, these layers are well defined, but in a red supergiant of this magnitude, they blur into one another. The core where fusion proceeds most intensely is small, compared with the overall radius, but contains much of the remaining mass. Around it, shells of lighter elements fuse in succession, releasing energy that supports the outer layers. Each zone represents a stage in the gradual exhaustion of fuel. At the center, temperatures reach hundreds of millions of degrees, sufficient for helium nuclei to combine into carbon and oxygen. This process, known as the triple alpha reaction, dominates once hydrogen is depleted. When helium runs low, the core contracts further, heating the surrounding shells. Hydrogen fusion continues in an outer region encasing the core, while deeper inside, heavier elements begin to form through fusion of carbon and oxygen. The result is an onion-like structure, though vastly more dynamic than the metaphor suggests. Each layer burns at its own pace, creating a hierarchy of energy sources that feed the entire star. The boundaries between them are not sharp surfaces, but gradients of temperature and density. Energy moves outward through radiation, until the opacity of the gas becomes too high, at which point convection takes over, carrying heat in rising currents of matter. In Stephenson 2.18, convection dominates nearly all regions above the core. Its envelope is so extended and low in density that radiative transport is inefficient. The gas moves in vast eddies that rise and fall slowly, carrying energy outward and mixing the chemical elements produced by fusion. This mixing enriches the outer layers with heavy elements, altering the star's spectrum and accelerating mass loss. Models suggest that convection may extend almost to the core, an unusual situation compared with smaller stars. This deep mixing ensures that the products of nuclear burning do not remain trapped, but are circulated toward the surface, where they will eventually be expelled into space. The immense size of the envelope means that energy takes years to travel from the core to the surface, even by convection. Within this time, conditions in the core can change significantly. As helium fusion wanes, the core contracts and heats, triggering new reactions. Carbon and oxygen begin to fuse, creating neon sodium and magnesium. Each successive stage occurs more rapidly than the one before, because the increasing temperature accelerates nuclear rates, but also raises the energy demand needed to support the growing weight of the overlying layers. This cascade continues until iron is produced, the endpoint of fusion under normal stellar conditions. Iron cannot yield energy through fusion. Once it accumulates in the core, collapse becomes inevitable. But for Stephenson 2-18, this stage remains in the future. For now, its structure remains marginally stable, maintained by the ongoing reactions in helium and carbon shells. Computational models use equations of state opacity tables and nuclear reaction rates to estimate the conditions inside such a star. From these, astronomers infer that the core of Stephenson 2-18 may contain several solar masses of carbon and oxygen, surrounded by shells where helium and hydrogen continue to burn. Above these layers, the density drops sharply, falling by many orders of magnitude toward the surface. The gradient is so steep that most of the star's radius contains only a small fraction of its total mass. In this sense, the visible bulk of Stephenson 2-18 is an illusion of scale, a vast, nearly empty envelope enclosing a dense core. The pressure within the core is balanced by radiation, but as the composition changes, the balance shifts. Degeneracy. the quantum pressure of electrons begins to contribute, marking the transition toward the final stages of life. Theoretical models of red supergiants indicate that such stars exist near a limit where radiation pressure dominates over gas pressure. This dominance makes them sensitive to small disturbances. A slight change in opacity or fusion rate can expand or contract the envelope dramatically. For Stephenson 2-18, whose luminosity approaches the Eddington limit stability, depends on the fine balance between energy generation and mass loss. Should the luminosity rise even modestly, the outer layers could be ejected entirely. Conversely, if mass loss reduces the envelope too much, the star might contract and heat, becoming a hotter, smaller object known as a yellow or blue supergiant. Observations of similar stars suggest that such transitions can occur over tens of thousands of years, brief moments by stellar standards. The internal structure is further complicated by rotation and magnetic fields. Though rotation slows as the star expands, residual angular momentum can influence convection, creating asymmetries in the flow of material. Magnetic fields generated by these motions may channel mass loss along preferred directions, contributing to the irregular shapes observed in surrounding nebulae. While direct measurements of Stephenson 2-18's magnetic field are not possible, models predict fields strong enough to affect the wind and possibly to influence dust formation. These subtle interactions within the interior shape the appearance and evolution of the star's outer layers, linking unseen processes at the core to visible phenomena at the surface. Because no light escapes from inside, the evidence for this structure comes indirectly through observations of temperature, luminosity, and composition. The presence of certain elements in the spectrum implies that fusion has progressed beyond hydrogen and helium. Ratios of carbon to nitrogen and oxygen reveal the degree of internal mixing, confirming that convection carries material outward. The enrichment of the atmosphere with heavier elements such as sodium and magnesium supports models predicting advanced burning stages. Each spectral clue adds to the picture of an interior layered by fusion and shaped by movement. Ultimately, Stephenson 2-18 exemplifies the principle that even the most immense structures obey the same physical laws that govern ordinary stars. Gravity compresses matter, fusion releases energy, and equilibrium holds until the balance fails. The difference is one of scale forces that act over kilometers in smaller stars operate here over billions of kilometers. The pressures and temperatures involved defy imagination, but follow predictable equations. The models that describe them are extrapolations tested against observation, refined with every new measurement of similar giants. Though uncertainty remains, they provide a coherent framework that explains how a star of such size can exist, however briefly. Inside this enormous body matter and energy flow in continuous exchange. The core contracts as it burns heavier fuels, the envelope expands in response, and the cycle of instability feeds upon itself. The interior is not a static arrangement of shells, but a living process evolving from moment to moment. Each nuclear reaction contributes to the grand equilibrium that sustains the star's light. That equilibrium, though destined to fail, persists for now, holding together a structure that should not endure by ordinary measures. In its quiet balance of gravity and fire, Stephenson 2-18 becomes both a question and an answer, proof that even within the boundaries of known physics, the universe still allows forms that seem impossible. Deep within the hidden core of Stephenson 2-18, matter is crushed to densities and temperatures that defy comprehension. Here energy is born. The immense gravitational pressure forces atomic nuclei together, overcoming the natural repulsion between positively charged protons. This process, nuclear fusion, is what sustains all stars, but Within Stephenson 2-18, it occurs on a colossal scale. The core, small compared with the star's overall size, acts as a furnace that manufactures new elements through successive stages of fusion. At its centre, helium fuses into carbon and oxygen through the triple alpha process, a reaction that requires temperatures exceeding 100 million degrees Kelvin. The result is the creation of heavier nuclei and the release of enormous amounts of energy, which flows outward, supporting the star against gravitational collapse. Around this central zone, shells of burning hydrogen and helium continue to operate, producing layers of energy generation that sustain the bloated outer atmosphere. Each fusion stage follows a predictable path governed by temperature and density. Once helium is depleted in the core carbon, an oxygen fusion ignite in shells closer to the center. These reactions create neon sodium and magnesium, all while emitting gamma-ray photons and energetic particles that help regulate the star's pressure. The reactions accelerate as the core contracts, each step lasting a fraction of the time of the previous one. Hydrogen burning endures for millions of years, helium burning for hundreds of thousands, but carbon and neon stages may last only a few thousand. In the final moments of such a star's life, fusion of silicon into iron proceeds in mere days. Stephenson 2-18 is not yet at this final stage, but its core is approaching the conditions where these reactions will begin. In the process, it becomes a factory of elements, continually enriching the interior with nuclei that did not exist when the star was born. The structure that results resembles an onion, though far more dynamic, an iron core that will one day form surrounded by shells, where silicon, oxygen, neon carbon, helium, and hydrogen burn in sequence. Each shell contributes energy to the whole, feeding the outward pressure that holds the star together. The deeper the layer, the shorter its lifetime, and the more intense its energy output. Fusion in these zones is so rapid that neutrinos, nearly massless particles that interact weakly with matter, carry away much of the energy. These ghostly messengers escape freely, providing the only direct signal of processes that will soon end in collapse. The physics of element creation in Stephenson 2-18 mirrors the universal sequence that has built the periodic table. In its earlier life, hydrogen fusion in the core produced helium through the proton-proton chain and the carbon-nitrogen-oxygen cycle. As the core temperature increased, helium began to fuse into carbon, a step that also produced oxygen through side reactions. When helium was exhausted, carbon burning created neon and magnesium, while neon burning yielded oxygen, and magnesium again through different channels. At each stage, the core grew hotter and denser. When these reactions can no longer produce net energy, the star will approach collapse. The cumulative result of these cycles is the generation of elements up to iron, the heaviest nucleus that can be produced by fusion without consuming energy instead of releasing it. Beyond iron, heavier elements require a different mechanism, one that will come only when the star ends its life in a supernova. The creation of elements is a continuous balancing act. In the core, gravity tries to compress matter endlessly while fusion pushes outward. The heat from fusion maintains the pressure that keeps the core from collapsing. Yet as each fuel source is exhausted, the balance shifts and the core contracts again, increasing temperature and density until the next reaction ignites. This rhythmic succession of burning stages defines the late life of all massive stars. For Stephenson 2-18, the transition between stages is accompanied by adjustments in luminosity and radius. When the core contracts and a new shell begins to burn, energy output rises, causing the outer envelope to expand. The star becomes even larger and cooler, while internally it grows more compact and hot. These alternating expansions and contractions are subtle on human timescales, but profound on stellar ones, shaping the star's path toward its final state. As fusion progresses, the byproducts enrich the surrounding layers. Convection mixes carbon, nitrogen, and oxygen outward, altering the chemical composition of the atmosphere. Spectroscopic observations reveal these elements in the outer regions, confirming that internal fusion products have reached the surface. This process, known as dredge-up, is common in evolved stars, but especially efficient in red supergiants, whose convective zones penetrate deep into the interior. The material released in the wind therefore carries the fingerprints of these reactions, isotopes of carbon and oxygen, traces of aluminum and magnesium and heavier nuclei that formed in brief bursts of high temperature. When this material escapes into space, it joins the raw matter from other dying stars, contributing to the chemical diversity of the galaxy. Fusion also influences the star's stability. Each stage releases energy in a distinct way, and when one phase ends abruptly, the change can trigger structural adjustments that ripple through the star. The outer layers respond to these shifts as subtle variations in brightness or wind strength. In extreme cases, instability can lead to violent ejections of matter. For Stephenson 218, the transitions are expected to be gradual, but the immense size of its envelope amplifies even small changes. The fusion engine at its core thus governs every visible feature, from the rhythm of its pulsations to the slow growth of its surrounding dust. At the atomic level, the processes within Stephenson 2-18 represent the fundamental story of cosmic evolution. The hydrogen that now fuels the outer shells was created in the first minutes after the Big Bang. Through fusion, that simple element becomes helium, carbon, oxygen, and beyond the ingredients of planets, oceans, and life. Every atom of iron in human blood, every grain of calcium in a mountain once passed through a star like this, or one that exploded long before Earth formed. Stephenson 2-18 stands as a living example of that creative cycle still in progress. It forges matter from energy storing within its core the elements that will someday be dispersed across the galaxy. Despite the immense power of these reactions, the star remains stable only as long as the outward pressure from fusion equals the inward pull of gravity. When fusion in the innermost regions ceases, that balance will fail. The core will contract, rapidly heating, until new reactions ignite, or until collapse becomes unstoppable. The final fusion stage, silicon burning into iron, will occur so quickly that it will pass unnoticed from any external viewpoint. For a few days, the core will churn with incredible intensity, generating as much energy as all the previous stages combined. But iron cannot sustain fusion. Once it dominates, the end will arrive. For now, Stephenson 2-18 endures in equilibrium, its inner furnaces hidden behind veils of gas and dust. The energy produced in the core travels outward through countless interactions, eventually emerging as the soft infrared light that reaches our telescopes. That light is ancient by the time it arrives, carrying within it the imprint of all the fusion that occurred before human civilization existed. To study it is to glimpse both the past and the future, the moment when matter transforms and the cycle of creation continues unbroken. Within its quiet glow lies the power that shaped the universe itself, the same process that will one day scatter the ashes of this star across the galaxy to begin again in another form. The slow balance that has sustained Stephenson 2-18 for millions of years is beginning to fray. Deep inside, the sequence of nuclear burning continues, each new stage shorter than the last. As heavier elements accumulate in the core, the rate of energy production accelerates while the reservoir of available fuel dwindles. The core contracts, the temperature rises, and the outward flow of radiation struggles to keep pace. For the moment, equilibrium still holds, but it grows increasingly fragile. The star's outer envelope, vast, diffuse and loosely bound, responds to every small shift in internal pressure. It expands and contracts in slow, rhythmic cycles, breathing in time with the hidden pulse of fusion. Each contraction compresses the core, further hastening the next phase of burning. Each expansion sheds more of the star's mass into space. This feedback loop defines the final era of red supergiant evolution, a period of magnificent luminosity paired with relentless decline. As Stephenson 2-18 ages, its core becomes a complex stack of active shells, each fusing a different element. Hydrogen and helium burn in the outer regions, while carbon, neon and oxygen burning proceed closer to the center. Each layer feeds energy outward, but also adds to the growing weight pressing on the core below. Gravity strengthens as the core contracts and temperatures soar beyond hundreds of millions of degrees. At such extremes, even brief changes can have vast consequences. The carbon-burning stage may last only a few thousand years, neon and oxygen burning perhaps hundreds. Each transition reshapes the internal structure, causing subtle tremors that ripple outward through the convective envelope. The result is an almost imperceptible variability in brightness, small to observers on Earth, but immense in absolute scale. The star's outer layers are now so extended that they verge on gravitational unbinding. The surface gravity is a fraction of that on the Sun, so weak that a gentle push of radiation can lift matter into space. Mass loss becomes the dominant process in the star's evolution. Every pulsation, every convective plume sends more material into the circumstellar envelope. Estimates suggest that a red supergiant at this stage can lose one solar mass every 100,000 years or less. For Stephenson 2-18, whose mass once exceeded 40 suns, this means it may already have shed a significant portion of its original material. What remains is a tenuous outer shell surrounding a contracting core, an enormous hollow structure whose stability depends on an increasingly exhausted source of energy. The signs of this transformation appear in the changing composition of the outflow. Infrared spectra reveal elevated levels of heavy elements such as magnesium, silicon and oxygen, all synthesized in the star's interior and now expelled in the wind. These elements condense into dust farther out, enriching the cluster's environment. The process continues silently but steadily, a quiet unraveling of one of the largest stars ever observed. Each year the envelope grows thinner. Each century the core grows denser. The energy balance narrows until only small adjustments are needed to tip it toward collapse. Yet the star persists in its enormous stillness, its faint red glow steady against the vastness of space. The physical cause of this instability lies in the nature of fusion itself. When lighter nuclei combine into heavier ones, energy is released because the binding energy per particle increases up to iron. Beyond that point, fusion consumes rather than liberates energy. As Stephenson 2-18's core evolves toward iron, it approaches a limit. The outward radiation pressure that once resisted gravity weakens. The core temperature rises, but instead of producing new energy, the reactions only hasten the inevitable. The outer layers, still governed by the radiation from below, lag behind the changes in the core. They continue to expand and cool even as the center begins its final contraction. The contrast between the tranquil surface and the turmoil within widens. To an observer across the galaxy, the star appears unchanged, but internally it is on the verge of irreversible transformation. In this phase, the timescales of stellar life compress dramatically. Millions of years of hydrogen burning give way to tens of thousands of years for helium, and now mere centuries for heavier elements. The entire remaining lifespan of Stephenson 2-18 may be measured in tens or hundreds of thousands of years, a brief instant in cosmic history. During this time, the envelope will continue to lose mass, forming an ever-thickening shroud of dust. This envelope, illuminated from within, will obscure the star's light almost entirely by the time collapse begins. Only infrared and radio wavelengths will penetrate, marking the star's existence as a diffuse source of heat within the Scutum arm. Eventually, when the core can no longer support itself, the entire structure will give way in a catastrophic implosion. The transition to collapse begins quietly. As the core contracts, electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. These neutrinos escape, carrying energy away faster than radiation can replace it. The loss of pressure support causes the collapse to accelerate, and within seconds the core density reaches that of an atomic nucleus. When this happens, the inward fall halts abruptly, and the core rebounds, sending a shockwave outward. This shockwave, strengthened by energy from neutrino interactions, tears through the surrounding layers, driving them into space. To distant observers, the star that had been invisible behind dust will suddenly brighten to outshine the entire Milky Way for a brief moment. The event will mark the end of Stephenson 218's life as a red supergiant, and its transformation into something far smaller but infinitely denser, a neutron star or a black hole. For now, these events remain in the future, concealed behind tens of thousands of years of apparent calm. The star continues its slow pulsation, its atmosphere expanding and contracting as though breathing. The infrared light we see today may come from an era long before even these final reactions began. The distance between observation and reality is measured not only in light years but in time. Every photon that reaches Earth represents a message from the past, a moment when the star was still stable. By the time its last light arrives here, the star itself may already have vanished. The end of stellar life is not an abrupt cut-off, but a sequence of transitions, each setting the stage for the next. Stephenson 218 is now in the last stable phase before core collapse, burning through heavier elements in concentric shells. Its core is shrinking, its surface drifting outward, and its winds thickening with dust. The processes are gradual yet inevitable, the natural consequence of physics unfolding across cosmic time. As the star approaches this final threshold, it embodies the paradox of massive stars. The greater their size and brilliance, the shorter their lives. In giving off so much energy, they hasten their own demise. The approach of death for a star like Stephenson 218 is therefore both decline and completion. It has already created and dispersed materials that will form future stars and planets. Its eventual explosion will scatter even more. The dust and gas that now veil it will one day become part of the galaxy's next generation of stars. Its destruction will not mark an end, but a transition in the endless recycling of matter. For the moment, however, it endures as a monument to stellar endurance, suspended between stability and collapse, immense quiet and fading a star nearing the conclusion of its long and luminous life. The final act of Stephenson 218's existence will begin invisibly deep within the unseen heart of the star. When the core becomes dominated by iron, fusion can no longer release energy. The reactions that once supported the immense weight above now drain heat instead of providing it. Gravity, no longer balanced by radiation pressure, takes command. The core begins to contract, first slowly and then with unstoppable acceleration. As it collapses, the temperature soars to billions of degrees, compressing matter beyond the density of an atomic nucleus. Electrons are forced into protons, forming neutrons, and releasing neutrinos in vast numbers. Within seconds, the core becomes a sphere of degenerate matter, only a few tens of kilometers wide, yet containing more mass than the Sun. The collapse halts abruptly when nuclear forces resist further compression. The sudden stop sends a shockwave racing outward through the overlying shells. It is in this moment that the energy built over millions of years is released all at once. The shockwave alone cannot unbind the star. It loses strength as it pushes through the dense material, but the flood of neutrinos streaming from the core deposits energy back into the outer layers, reviving the wave. The result is a supernova, one of the most powerful events in the universe. For a brief time, Stephenson 218 will shine as brightly as an entire galaxy. The dust that once hid it will be blasted away, revealing the explosion across space. Even from 20,000 light-years away, the outburst would be visible to telescopes as a new point of light in the constellation Scutum, fading over weeks, but leaving behind a nebula of glowing gas. This event will release more energy in a few seconds than the Sun will emit in its entire lifetime. The star's vast outer layers, once held in tenuous equilibrium, will be hurled outward at thousands of kilometers per second, enriching the surrounding cluster with freshly forged elements. Inside the collapsing core, the fate depends on mass. If the remnant after the explosion remains below about 3 solar masses, the neutrons will resist further collapse, forming a neutron star, a sphere so dense that a teaspoon of its matter would weigh billions of tons. If the remnant is heavier, even neutron pressure will fail, and gravity will compress it beyond all known physics, creating a black hole. Given its original mass and the amount lost through winds, Stephenson 218 likely sits near this threshold. It may leave behind either a massive neutron star spinning rapidly and radiating beams of particles, or a silent black hole hidden within the remnants of its own destruction. Whatever the outcome, the star will cease to exist as a luminous body, replaced by the expanding shell of debris that marks its passing. The supernova will not occur without warning, though those signals would be subtle. In its final months, the star's brightness may fluctuate erratically as convection and nuclear burning fight for equilibrium. The neutrino flux would increase dramatically, invisible but detectable by instruments on Earth if the distance was smaller. Shock waves within the core may cause the star's outer layers to tremble, ejecting additional material just before collapse. When the explosion finally arrives, it will unfold over seconds but reverberate across millennia. The first sign would be a sudden burst of neutrinos, followed minutes later by the flash of light as the shock wave breaks through the surface. The surrounding dust would briefly illuminate, reflecting the glare like a halo. The cluster around it, filled with other red supergiants, would be transformed as the blast sweeps through, compressing and heating the interstellar medium. Some of this material might trigger the birth of new stars, continuing the endless cycle of creation from destruction. The physical mechanics of the explosion are governed by fundamental laws of energy transfer. As the core collapses, gravitational potential energy is converted into heat neutrinos and kinetic motion. 99% of the energy escapes as neutrinos, but the remaining fraction, still immense, is sufficient to propel the outer layers outward. The velocities involved can exceed 10,000 kilometers per second. The ejected material carries heavy elements formed during the explosion itself. Through rapid neutron capture, known as the R-process nuclei, heavier than iron are created in microseconds, including gold, platinum, and uranium. These atoms scattered across space will one day be part of future worlds. The death of a single star thus seeds the galaxy, with the ingredients of planets, oceans, and living systems. After the initial explosion, the remnants expand and cool, forming a supernova remnant, a glowing nebula of gas and dust. Shock waves interact with the interstellar medium, generating radio and X-ray emissions that can persist for tens of thousands of years. The core remnant, if a neutron star, may spin rapidly and emit pulses of radiation, becoming a pulsar. If it becomes a black hole, it will vanish into darkness, detectable only by its gravitational influence, or by the X-rays emitted as surrounding gas falls inward. In either case, Stephenson 218's identity as a star will end replaced by an object far smaller but infinitely more extreme. The cluster that once contained one of the largest red supergiants in the galaxy will then host a remnant of extraordinary density, a compact echo of what was once vast beyond comprehension. From Earth's perspective, the supernova's light will not arrive until long after it has already occurred. Because the star is about 20,000 light-years away, the explosion we will eventually witness has likely not yet happened, or perhaps it already has its light still crossing the void toward us. When it finally arrives, humanity may be very different, yet the photons and neutrinos will carry the same message: the transformation of mass into energy, the recycling of matter from one form into another. Observatories across the electromagnetic spectrum will study the event, measuring the expansion velocity, luminosity, and spectral composition. These data will reveal the internal structure that existed moments before collapse, providing clues about how the most massive stars end their lives. For the Stephenson 2 cluster, the death of such a member will have lasting effects. The shockwave will sweep away gas and dust, possibly triggering compression in nearby regions that could lead to new star formation. The expelled material will enrich the cluster with heavy elements, altering the chemistry of any future generations. Over millions of years, the remnants will merge with the general interstellar medium, indistinguishable from the background, until another collapse repeats the cycle. The legacy of Stephenson 2-18 will live on not as a single object, but as countless fragments dispersed through space. The prospect of this supernova underscores the brevity of massive stellar life. Stars of great mass burn intensely and die young, converting their fuel in mere millions of years compared to the billions that sustain smaller suns. Stephenson 2-18's immense luminosity is both its glory and its undoing. By shining so brightly, it hastens its exhaustion. The collapse that awaits it is not an anomaly, but a natural outcome, a final stage in the universal process of stellar evolution. When it comes, the event will be violent yet necessary, turning what was once a single body into the seeds of future creation. In the quiet present before that explosion, Stephenson 2-18 continues to radiate softly through dust, a red beacon nearly lost in the glow of the Scutum arm. To the galaxy, it is both ancient and brief, a transient phase between two eternities. Its collapse will someday illuminate the night for a fleeting moment, and then fade, leaving behind only traces, a cloud of expanding debris, a pulse of neutrinos, perhaps a black hole where light itself cannot escape. The cycle will continue the matter of the star returning to the Milky Way that gave it birth, ensuring that the story of its life will never truly end. When Stephenson 2-18 finally ends its life, the consequences will ripple far beyond the boundaries of the star itself. The blast of its supernova will not simply erase the star, it will remake the environment from which it was born. Within the Stephenson 2 cluster, the explosion will send shock fronts racing outward at thousands of kilometers per second, compressing and heating the gas between the surviving stars. These waves will collide with the winds and envelopes of neighboring red supergiants, stirring the cluster into a transient chaos. For a time, the region will shine in high-energy light as the supernova remnant expands, illuminating the surrounding dust. Then, as the debris spreads, the cluster will settle into a new equilibrium, its chemical composition permanently altered by the material the star has expelled. Every atom once trapped inside Stephenson 2-18 will be redistributed, joining the diffuse, interstellar medium that threads through the Scutum arm. Oxygen, silicon, magnesium, iron elements forged in the heart of a dying giant will drift through the galaxy for millions of years, mixing with the gas clouds that spawn future stars. In this way, the death of one star contributes directly to the renewal of the Milky Way. The material ejected from massive stars provides the heavy elements that smaller, longer-lived stars incorporate into planets and life. Without generations of supernovae enriching the galaxy, there would be no rocky worlds, no water, no carbon-based chemistry. Stephenson 2-18, by living and dying on such a monumental scale, becomes one participant in that cosmic recycling. Its remains will travel far, carried by galactic rotation and turbulence, spreading across thousands of light years. Over vast spans of time, its atoms will become part of molecular clouds, then of new stars and planetary systems. Some fraction of its material could one day be part of another living world, orbiting a smaller sun somewhere within or beyond the Milky Way. The legacy within the cluster will also be structural. When one massive member of a cluster explodes, it can influence the stability of the remaining stars. The shock wave will clear away residual gas, potentially halting further star formation within the cluster's boundaries. Yet at the edges, where compressed gas collects new pockets of collapse, may begin creating smaller clusters or isolated stars. The Stephenson 2 cluster is already a product of an earlier wave of star formation. Stephenson 2-18's death will contribute to the next. In this way, massive stars act as engines of galactic evolution, alternately destroying and creating the conditions for birth. The process is slow from a human perspective, but steady across cosmic history. Each generation enriches and refines the next, increasing the metallicity of the galaxy over billions of years. Astronomers studying the aftermath of similar explosions observe that supernova remnants can persist for tens of thousands of years before dispersing. During that time, the expanding gas glows in multiple wavelengths, from visible emission lines to X-rays. The remnant of Stephenson 2-18 would likely become such a structure, perhaps resembling the great nebulae seen in other parts of the sky. Over time, as the shockwave slows, it will blend into the interstellar background, leaving only a faint bubble of enriched material. The cluster itself will gradually dissolve as gravitational interactions between its stars cause them to drift apart. In a few 100 million years, the individual members will be scattered through the Milky Way, and only through chemical tagging, tracing their shared elemental fingerprints, will it be possible to identify them as siblings. Among those scattered stars will be the enriched remnants of Stephenson 2-18, invisible yet enduring in composition. The role of such stars in shaping galactic chemistry cannot be overstated. They are the principal sources of oxygen and other heavy elements that dominate the periodic table beyond helium. Through both their steady winds and explosive deaths, they define the ratio of elements that determines the structure of galaxies, the cooling of gas clouds, and the formation of planets. Without them, galaxies would remain dim collections of hydrogen and helium, devoid of the complexity that allows life. Each red supergiant therefore serves as a bridge between the simplicity of the early universe and the diversity of the present one. Stephenson 2-18, among the largest of its kind, magnifies that role. Its contribution will not be measured in its brilliance, but in the atoms it leaves behind. The legacy also extends to the science of observation. Even before its death, Stephenson 2-18 has already changed how astronomers understand the limits of stellar physics. Its immense size challenges models of how much a star can expand without disintegrating. The uncertainties surrounding its radius, luminosity, and mass loss have spurred refinements in theoretical modelling of stellar atmospheres and convection. Instruments capable of observing it through heavy extinction have driven advances in infrared astronomy. Future telescopes will continue to monitor the region, looking for signs of variability or change that precede collapse. When the supernova eventually occurs, it will provide data critical to testing how massive stars evolve and die. The light curves, spectra, and chemical yields will inform models of element production and energy transport, completing the story that began with its discovery. The Stephenson 2 cluster itself will continue to age. As its most massive stars die, only intermediate mass and smaller stars will remain shining for billions of years. These survivors will preserve the memory of the cluster's formation in their motions and compositions. Observing them will allow future generations to reconstruct the history of this region long after the giants have vanished. Even when the name Stephenson 2-18 has faded from catalogues, its influence will persist in the data in the chemistry of new stars and perhaps in the rocks and atmospheres of worlds yet to form. On a larger scale, the Milky Way absorbs these contributions quietly. Every supernova adds trace amounts of metals astronomers term for elements heavier than helium to the galactic disk. Over cosmic time, this enrichment transforms the appearance and behavior of the galaxy. Stars born in later epochs contain higher metallicities, meaning they form planets more readily and evolve differently than their ancient predecessors. The light from these younger stars is subtly altered by the very elements that once resided in massive red supergiants. Stephenson 2-18 thus participates in a continuum that extends backward to the first stars and forward to those yet unborn. Its atoms will circulate indefinitely, reshaped by time but never lost. From the human perspective, such a legacy is almost invisible, unfolding over scales that dwarf any civilization. Yet in the quiet arithmetic of stellar evolution, it is inevitable. The gas and dust expelled by dying giants collect into clouds. The clouds collapse and new stars ignite, beginning the cycle again. The materials that compose the Earth, the iron in its core and the oxygen in its air, all trace their ancestry to similar stars that perished billions of years ago. Stephenson 2-18 will someday contribute to that ongoing lineage. It is a reminder that even the most distant and short-lived of objects leave an imprint that endures. When the light of its final explosion fades, there will be no monument, no visible trace of the star's existence, except the enriched dust mingling with the galaxy's background. Yet that dust will carry the memory of its life, the radiance it once emitted, the elements it forged, and the energy it released. Through these remnants, Stephenson 2-18 will continue to shape the Milky Way long after it is gone. Its legacy is not the moment of destruction, but the slow diffusion of its matter into everything that follows. In this way, the end of one immense star becomes part of the endless continuity of the cosmos. Long before its end, Stephenson 2-18 has already altered our understanding of what stars can be. Its discovery was not a single moment, but a gradual revelation piece by piece through layers of dust and doubt. For decades it hid behind the dense clouds of the Scutum arm, invisible to optical telescopes and unrecorded in early surveys. Only with the development of infrared astronomy did its faint glow emerge, first as an unidentified bright source, then as one point among many in a crowded cluster. As technology advanced, astronomers realized that this seemingly unremarkable object possessed properties far beyond ordinary scale. The light curve, the spectral profile, and the inferred luminosity pointed towards something unprecedented, a red supergiant so immense that even theoretical models strain to accommodate it. Stephenson 2-18 thus became both an astronomical object and a scientific challenge, a test of the boundaries of stellar physics. The act of observing it reveals as much about human ingenuity as it does about the star itself. Because visible light is almost entirely absorbed by interstellar dust, astronomers must rely on longer wavelengths. Infrared detectors aboard space telescopes immune to atmospheric interference gather photons that have travelled 20,000 light-years to reach their sensors. Each pixel of data represents the survival of light through countless collisions and absorptions. The interpretation of that data depends on models of extinction temperature and distance refined through comparison with other red supergiants. Even with such corrections, uncertainty remains, but within those uncertainties lies progress. Every observation narrows the range of possibilities, turning the star's incomprehensible scale into quantifiable, if still astonishing, numbers. Observing Stephenson 2-18 is also an exercise in patience. Its variability unfolds over years, its light crossing millennia before reaching us. The state we see today corresponds to events that occurred when early humans were still shaping tools from stone. To study it is to peer not just across space but across time into a chapter of the universe long before written history. The photons we record now left the star when Earth's climate, continents, and ecosystems were vastly different. In this sense, every measurement is a form of archaeology, excavating the ancient light that carries information about conditions long past. Yet because the star evolves faster than the light that reaches us, it is possible that the Stephenson 2-18 of the present no longer exists in the form we observe. It may have changed or even ended its light still en route through interstellar darkness. The tools used to study it continue to evolve. Ground-based observatories with adaptive optics now complement space-based instruments, providing sharper images despite the distortion of Earth's atmosphere. Spectrographs divide its light into thousands of narrow bands, each revealing a piece of its composition. Radio telescopes detect the molecular emissions from its surrounding dust, mapping the shape and velocity of its wind. Data from these sources combine into a multidimensional picture, a star not as a single point but as a dynamic structure embedded in a complex environment. Through such observations, astronomers can trace the flow of matter from the core to the outer envelope and beyond. Every measurement refines the models of stellar evolution, bringing theory and observation into closer alignment. Human perception, however, is ill-suited to scales of such immensity. Distances measured in light-years, temperatures of millions of degrees radii exceeding billions of kilometers all exceed the realm of direct experience. To make sense of Stephenson 2-18, astronomers translate numbers into comparisons. If placed where the Sun is, its surface would extend past Saturn. Its luminosity would illuminate the solar system brighter than daylight. These analogies bridge understanding but also underscore limitation. The true nature of such a star cannot be comprehended through imagery alone. It must be approached through abstraction, through the language of physics. And yet, even stripped of metaphor, the reality remains profoundly humbling. From the standpoint of science, Stephenson 2-18 is valuable for what it reveals about the extremes of stellar evolution. From the standpoint of human perspective, it represents something deeper, the scale of the universe beyond human significance. Its existence challenges assumptions about stability, permanence, and proportion. The sheer size of its atmosphere, the time required for its light to reach us, and the inevitability of its destruction all emphasize how transient even the greatest structures can be. For all its enormity, Stephenson 2-18 is fleeting. Within a few 100,000 years, a blink in cosmic history, it will collapse and vanish, leaving only a cloud of enriched gas. Yet for the duration of that brief existence, it embodies the full range of stellar possibility from creation to dissolution. Astronomers studying it today stand at the intersection of knowledge and wonder. The instruments they build extend the reach of perception, turning invisible wavelengths into images and numbers. But behind the data lies a quieter motivation, curiosity about how the universe organizes itself, how matter evolves from simplicity to complexity, and how such balance can persist at scales beyond imagination. Stephenson 2-18 provides one of the purest examples of that balance. Its core burns with ferocity while its surface drifts in near weightlessness. Its light fills space yet remains almost entirely unseen. To describe it scientifically is to enumerate forces and equations. To contemplate it is to acknowledge the vastness in which we exist. The study of such stars also connects generations of inquiry. Observations of Betelgeuse, Vuae Caenia Majoris, and now Stephenson 2-18 trace a continuum of discovery stretching back centuries. Each instrument, each survey refines what came before, adding to a cumulative understanding of how massive stars live and die. The data gathered from Stephenson 2-18 will inform the next models of stellar atmospheres and mass loss, improving predictions for other red supergiants nearing the end of life. In this way, even before its death, the star contributes to science as a living laboratory, shaping how future astronomers interpret their findings. There is also an emotional dimension to observing something so distant and ephemeral. Knowing that the light we see left the star long ago, that we are witnessing an ancient state already gone, transforms observation into reflection. The calm red glow captured by telescopes speaks of power and fragility intertwined. It reminds us that creation and decay coexist at every level of nature. The same processes that will one day destroy Stephenson 2-18 are the ones that made Earth and every living thing upon it. Each photon from the star is a fragment of that story, a particle of history travelling across time to illuminate the present. For humanity, Stephenson 2-18 serves as both subject and symbol, a subject of rigorous study bounded by physics and observation, and a symbol of the universe's vast continuity. Long after it fades from view, its influence will endure in the galaxy's chemistry, in the theories refined by its example, and perhaps in the collective imagination of those who look upward and wonder how something so immense could ever have existed. In the night sky, unseen to the eye yet known through instruments, it remains a quiet reminder of scale, a testament to the silent, enduring processes that shape the cosmos. To observe it is to witness a moment within that process, a glimpse of light travelling from a giant whose time is nearly over, but whose story will never truly end.